Hello, here we will use the main result on the symmetric polynomials to figure out the answers for the discriminants of polynomials of a small degree. I'll start warming up with the quadratic case. I'm still assuming that my polynomial is monic, the leading term is 1. I have coefficients b and c, and the discriminant always is the product of the differences of the roots squared. So I only have just one difference, having two roots. And the general method of determining the expression in terms of elementary symmetric polynomials of this particular symmetric polynomial is as follows. I have to start with the leading monomial in my symmetric polynomial. So here it is x1 squared, because I have to take the leading monomial inside the square and then just square it. So everything else will be smaller in this lexicographical sense. The leading monomial has powers 2 and 0 for variables x1 and x2 I have. And all other vectors which are smaller in lexicographic sense than these and still non-decreasing I have to list now. And there is just one more, 1, 1. And then I have to imagine elementary symmetric polynomials with leading monomials labeled by those vectors, and the process is as follows. So we'll start with sigma 1, and it has to come in the power which is the difference of the two coordinates, the first and the second, so that will be 2. And then we have to follow with the power of sigma 2, which is the difference of these and none, so that will be really still 0. Here we have sigma 1 to the power which is 1 minus 1, so no sigma 1, and sigma 2 to the power 1. And then we have to determine the coefficients with which these products of elementary symmetric polynomials appear. And the leading coefficient for the overall maximal monomial is 1, and it has to match with the leading coefficient here, which is also 1. So we know the coefficient here, but we don't know it here. So we'll just use pencil to put alpha here. Now I have to determine this one unknown alpha, and the easiest way to do that is to evaluate. Let me take the values x1, x2, all being 1. The discriminant on those values is 0. On the other side I'll have sigma 1, which is the sum. So I'll just remind myself what is sigma 1. It's the sum. And sigma 2 is the product. And the sum of 1 and 1 will be 2, and it has to be squared. And then the product will be 1, so I just see my alpha. Alpha from here is negative 4, so that's what alpha is, negative 4 here. And the final push is to write down the answer in terms of the coefficients. So this is the sum of roots. This is negative b, and it has to be squared, so negative b squared is as good as b squared. This is the product of the roots. This is c. So we recover the well-known formula for the discriminant of the quadratic. Let's now do the real thing. Let's do it for generic monic cubic. Here is its squared, here is its shape. B and C and D are some coefficients. The discriminant is the product of now 3 differences of the roots. The process is still the same. We start with the largest monomial, we record its vector of powers, and we go from there. So the largest we can manufacture by taking the largest monomial in each of the factors and then taking squares of them. So x1 squared is the largest in the first, x1 squared again is the largest in the second, x2 squared is the largest in the third. All in all, we'll have x1 to the 4, x2 squared, and no x3. Everything else will be smaller. The vector of powers is 4 and 2 and 0. So let me write it from a new line, I will have to list first all the vectors which are smaller than this, but still vectors of largest monomials in some symmetric polynomials. For that sake, they have to have coordinates which are non-decreasing. So I'll have to list all vectors which are smaller than this in lexicographical sense and then non-decreasing. And the process is industrial. We just start with the rightmost pile, imagining this number as a pile of height 2, and take one piece of a pile and move it to the right, still retaining the property that the vector is non-increasing. So that is the vector we get by moving one of those 2's to the right. We can't do any more moves from this pile because it's already as high as this. We have to start all over again with this pile and move one of those 4's to the right. This way we'll get 3, 3, 0. And then we can take either this or this as the input and move one of these 4's to the right one step. So we'll have 3 and 2 and 1. And then we can move one of these 3's to the right one more time, and that will be 2, 2, 2, giving us 2, 2, 2. And that is all that we can manufacture. So this is the complete list of vectors which are less than this, but still non-increasing. Now we have to write down corresponding products of symmetric polynomials. So here it is sigma 1 to the power 4 minus 2 squared times sigma 2 to the power 2 minus 0, 2, and no sigma 3. Here we have sigma 1 cube, sigma 2 to the power 0, sigma 3. Here we have just sigma 2 cube. Here we have sigma 1, sigma 2, sigma 3, all of them. And here we have sigma 3 squared. And again, I'll just put some unknowns here. Alpha, beta, gamma, delta. So I'll keep one line for the final answer in terms of the coefficients, but the task now is to determine this alpha and beta and gamma and delta. We'll start by recalling what sigmas are on my 3 variables. So the commas in between. This is just the sum. This is the sum of the products. This is just one triple product. Okay, and then I have to, as before, determine my unknowns by, say, clever evaluation. So I will imagine a collection of numbers, so really I have 4 knowns, I have to imagine 4 collections of values for x, which will be easiest for my purpose. So the first collection of values for x, I'll imagine such that it will only keep sigma 2 alive, and make others to sigma 1 and sigma 3, make them zeros. So it's easy to make sigma 3 0, just one of the x's to be set to 0 will do it. And to make sigma 1 0, I just need to choose the remaining 2 x's to be the same. So here's my collection for x1, x2, x3. I will just choose 1, -1 and 0. So then sigma 1 will be equal to 0, sigma 3 will be equal to 0, and then sigma 2 will be the sum of all products, and only one product will survive, will be -1. So I'll also list the value for delta. Delta is this, and the delta on this collection with the discriminant will be -1, and I'm sorry, I'm a bit slow here. So I have to take the sum of the products of all the variables in here. So it will be the differences. Sorry, I'm looking at the wrong place. So I have to evaluate this discriminant on the collection. So I'll have to take 1 without 0. Actually, it's 1 without -1 squared. So that gives me 4 already, but then 1 without 0 gives me 1, and then negative 1 without 0 gives me still 1. So all in all I have 4. And I can put it immediately to use. What do I get if I evaluate both sides of my equation on this collection of x's? So 4 on the left side, on the right, sigma 1, sigma 3 are zeros. This term is 0, this term is 0, this term is 0, this term is 0. Only one term for beta will survive. So 4 is equal to beta times the cube of sigma 2, the cube of negative 1. So that will be negative 1 as well. Which gives me the answer for beta. It is negative 4. Here it is. I'll proceed now with the second choice for x's. I will choose them to be such that still sigma 1 is 0, so that is just the sum. And then sigma 2 and sigma 3 are non-zero. So sigma 2, it's the sum of all products, will be negative 2, and the 1. The overall damage is negative 3. And then the product of all the coordinates will be negative 2. And the discriminant will be 0 because 2 of my inputs are the same. So plugging it into my equation, I'll have 0 on the left. Now sigma 1 is only 0, so all the terms containing sigma 1 will go away and I will be left with 2. One of them with coefficient delta, the other with coefficient which I know already. Negative 4 sigma 2 cubed, so sigma 2 is negative 3. I'll just write it as it is, negative 3 cubed. And then delta with coefficient sigma 3 squared, negative 2 squared. So look what happens, negative 2 squared is 4, and I have 4 again, and I have minus and minus cancelling out, so I can cancel 4 out, and then delta will be matching with negative 27. So that's what delta is, negative 27. The next choice is 2 and negative 1. So the choice is designed in such a way that sigma 2 is vanishing. It is vanishing because I have to take 2 with minus 1, 2 with minus 1, and then 2 with 2 in a sum. And that will give me negative 2, and positive 4. So overall will be 0 for sigma 2. The sum, however, will not be 0, and the product as well. So the sum will be positive 3, and the product will be negative 4. And the discriminant will still be 0 because the two first coordinates are the same. So writing the equation now, I'll have 0 on the left, still 0 on the left. And every time I have sigma 2, I have 0. So not this term, not this term, not this term, but these two will only survive. So I'll have alpha sigma 1 cubed times sigma 3. 3 cubed, and then sigma 3 is negative 4. And then I have negative 27 sigma 3 squared. So sigma 3 is negative 4, has to be squared. So now what happens, this is 27, this is 27, can be cancelled out. This is 4 squared, this is negative 4. Cancelling out, I will have alpha matching with negative 4. I'm down to just one unknown gamma, and to determine it I will take values all 1 for my x's. Sigma 1 on those values will be 3, sigma 2 will be sum of all 3 products will be still 3, sigma 3 will be 1, the discriminant will be 0. So this is the largest equation. I have all my terms surviving, so I have to see them all. Sigma 1 cubed, sigma 2 cubed, I'll just write what it is, 3 squared times 3 squared, not cubed by squared. And then negative 4 sigma 1 cubed, sigma 3, so I'll have 3 cubed and then 1. Negative 4, 3 cubed again, And then gamma, my unknown gamma, sigma 1, sigma 2, sigma 3, 3, 3, 1. I just write it as a 3 squared. And then negative, I'll write it as 3 cubed times sigma 3 squared times 1. So that is the equation from which I will recover my gamma. I can cancel out 3 squared, right? Because it's all the terms contain it. So I'll have 3 squared minus 4, matching the 0. Minus 4, 3 squared times 3 minus another copy of 4 times 3 plus gamma minus 3. And what can I do? I can, I can put gamma on one side and keep everything on the other. So what is this together? It will be 8 times 3. And then I have another copy of 3, and then I have this negative sign 3 squared. So this is as good as, say, 9 times 3, and then I'm subtracting another 9. So I'm really looking at 9 times 2, which is 18. That's my gamma. And that is with plus. So that is the last missing term. And now I'm ready to write the answer in terms of the coefficients. So the coefficients are almost elementary symmetric functions of the roots up to signs. Let's start from the 0 degree coefficient is the product of the minus the roots. So it will be minus sigma 3. This is plus sigma 2. Signs change in the other formulas. And this is still minus sigma 1 for b. So that's how I can substitute my coefficients in the formula here. Sigma 1 is negative b, but squared, it will still be b squared. Sigma 2 is positive c, so I have c squared. Negative 4, sigma 1 is negative b, so it will be negative b cubed. Sigma 3 is negative d, overall will be b cubed d. Sigma 2 is c, so I have negative 4c squared, sorry, c cubed, right? Sigma 2 is cubed. Then with coefficient 18, I have the product of all of them. Again, this is negative b, this is negative c, this is, sorry, negative d, this is positive c, will be 18 times b, c, d. And then with negative 27, I have sigma 3 squared. Sigma 3 is negative d, but squared it will be just d squared. So that is the compact answer in terms of coefficients for the discriminant of a polynomial of degree 3. See you later.